to Porous Media Tea Time Talks. We are part of Interporian Academy and we aim to spread the Porous Media science among young researchers. I'm Nara from the Federal University of Uberlândia in Brazil, and today in the studio with me we have Federico from PrincetonU and Marcel and Mohammed both from University of Oslo. And please feel free to subscribe to our channel and stay tuned to our talks. Today we are going to have two great presentations from Christopher and Zaid. At the end of each presentation, we are going to have 5 minutes for questions and answers. So we appreciate your participation in the chat box on the right hand side. Our first speaker is Christopher. He will talk about elastic turbulence generates anomalous flow resistance in porous media. He completed his bachelor's in chemical engineering at Purdue University studying surface adhesion and explosive detection. He then completed his PhD in chemical engineering at Princeton University, where he studied viscoelastic and elastic turbulence in porous media, as well as invasion percolation and hydrogel mechanics. He is currently a postdoctoral scholar at the University of California, studying active turbulence in pneumatic fluids. So, Christopher, you are welcome and the floor is yours.
All right, well, thank you so much for that introduction, and I'm really excited to be kicking off this session of Porous Media Tea Time. I'm going to be telling you guys today about a particular type of flow called elastic turbulence, which you can get for some types of viscoelastic polymer solutions, particularly in complex 3D porous media, which we'll get into. And I'll just start by kind of giving you this image here that is maybe very familiar to you of a stratified medium. And what you're visually seeing here is different grain sizes. And you can imagine as fluids move through these, just for a variety of environmental flows or industrial injection processes, that's going to affect the flow in a lot of ways. And so in particular, what I'm thinking about is not that surface kind of cartoon image I showed you, but really something much deeper. So this is kind of the type of geometry that you'd be thinking about for things like groundwater remediation, oil recovery, or geothermal energy extraction. In all of these, you have some kind of resource deep underground in a complex 3D porous medium. In general, you want to extract something like in oil recovery, you're trying to remove an oil. In groundwater remediation, you're trying to kind of sweep away a contaminant that is often oily. In geothermal energy extraction, you're trying to get heat. And you need to kind of evenly access a lot of the porous medium. And you can imagine that this is going to be complicated by the fact that these media are heterogeneous and have structure to them. And so here's just a simple cartoon of one of those types of heterogeneities, and that is stratification, which you can just imagine at the simplest level is just a difference in grain size. And so you can imagine here I have just two layers. I'm just imagining that they're equivalent, just kind of stacked on top of each other. And if you inject flow at some velocity, it's going to partition between those two layers. And your intuition tells you that it should be going more through the larger grains. And that's because the pressure gradient should be equivalent. If you're just flowing a Newtonian fluid, the velocity or the viscosity is constant. And that means that any differences in the permeability are going to be directly offset by a difference in the velocity. And what this means is if you inject something, here I'm just injecting a green dye, you can see that it moves really quickly through the coarse layer and is moving really, really slowly through the fine layer. So if this is one of these kind of three processes I've outlined, and you want to access your whole porous medium, you have to wait for the slowest layer. And if you have, many layers, you may be waiting a long time for it to access that slowest layer. And so what I'm going to be telling you about today is ways that you can kind of break this dependence. And the way we're going to do that is finding something that allows us to tune one of these other parameters in this Darcian law that I wrote down, which is the viscosity. And so one of the ways you can do that is by adding polymers. Most polymers, I'm sure many of you are aware, are shear thinning. And so here's an example. I'm actually going to use high molecular weight polymers. Here is that kind of resistance that you measure. So this is kind of taking this viscosity and getting an effective resistance for different shear rates. As you add polymers, you get a higher viscosity, and actually that viscosity kind of drops off at higher flow rates or at higher shear rates. And that's what you're kind of seeing here. It's kind of decaying slightly. So that's actually going to make the situation a little bit worse. But what some people have observed is for high molecular weight polymers, you see instead a very striking anomalous increase in the flow resistance. And so this is potentially a way where you can kind of add resistance maybe to one of the coarser layers to kind of help redirect the flow. The problem is that we don't really understand what's going on at all. So there's no way to kind of control this and do this in a targeted way in these complicated media. In fact, this has been observed for over 50 years, and there's still no models to predict when or how much of an increasing anomalous resistance you have. And so the trick is to develop some kind of simplified experiment where we can actually image what's going on in these complicated media. And so here is the test polymer solution I'm going to use. I'm going to use a Boger fluid, which just means that you can this is measuring the shear stress as a function of shear rate, and the fact that this is essentially a flat line is telling you that this is essentially a constant viscosity. It's actually decaying a little bit, which we model and account for, but you can kind of forget about that. The only important part about this fluid is that it's viscoelastic. And so here I'm measuring the first normal stress difference. This is a metric of how elastic the polymer is. And so this power law attendance tells me that as I increase the flow rate, the polymers are stretching and storing elastic energy, and that's going to modify the flow in important ways. And then I'm going to inject this into a 3D porous medium, which is just a granular packing of glass spheres that I've lightly centered together to create a static, centered, non-moving porous medium. And then because I've kind of selected the solvent very carefully, the solvent is completely transparent when it's injected into the medium. And so here you can, the beads you can't see at all because I've matched the refractive index with the glass. So now what we can do is image directly inside of individual pores. So what you're looking at is in this black space, this is the spherical grain. So here you can see there's 5 spherical grains. And then in the center in green, you're seeing the void space of the pore with passive tracer particles mapping out the instantaneous velocity of the flow within this medium. So now we can do this all over and kind of get an image of what's happening at the pore scale and at larger scales, which is very exciting. So here's kind of the first images of what these flows actually look like when you have a polymer solution flowing through a porous medium. And so this probably isn't very surprising to you guys at all. This is just the laminar flow of a polymer solution at low Reynolds number. So this is exactly what you expect for a Newtonian fluid. I've sped this video up a lot, but the streamlines aren't moving. The flow is generally left to right, as it will be in all of these videos I show you today. And the flow is laminar, of course, because the Reynolds number is very low. So we expect to see this kind of steady laminar flow. This is different if I crank up the flow rate a little bit. So I'm still at low Reynolds number. Anybody just from an engineering blind background might have told you that this should be a laminar flow, but when you actually image the flow, instead you see this really rich dynamic flow that's changing in time. And we can let this go for hours and hours, and we'll continue doing this. I've actually done this for 2 days before, and the flow keeps fluctuating, right? So this has reached some kind of dynamic steady state, and many people, not just me, have kind of drawn a loose analogy between this fluctuating flow state and turbulence. So here, this GIF I'm showing you here is inertially caused turbulence in the atmospheric boundary layer, and perhaps there's some kind of high-level similarities in the subtle eddies you see forming up here and jet streams with the eddies and jet streams you see in this turbulence, at least from a very kind of qualitative image. But here we have a different instability driven instead by elasticity, not by inertia. And so instead of using Reynolds number, the appropriate parameter we're going to use is a Weisenberg number, which is talking not about inertial stresses, but elastic stresses. Great. And then some people call this elastic turbulence, just to kind of hearken to this analogy, which may or may not be useful for us. But what we want to do really is think, how quantitatively can we compare this to turbulence? And if we can compare it quantitatively to turbulence, does that give us any new useful tools as engineers? And so the first thing I'm going to do is I'm going to actually quantify these flows. I'm going to do particle image velocimetry to map out the instantaneous velocities and then watch how they change in time. Here I'm just showing you one example pore, but I've done this all over the medium in many randomly selected pores. And here what you're seeing, this heat map is the fluctuating component of the velocity field. So in purple, you're seeing regions of the flow that are very close to the laminar speed. And in yellow, you're seeing the speed difference between the laminar and the instantaneous. You can see there are these kind of structures that are appearing and disappearing transiently. And just another way to visualize the same video is to take a strip of these pixels and stretch it out in time. So this is showing you how those bursts are kind of growing and decaying in time. And you can begin to identify that they have a certain kind of scale to them, maybe in length and in time, that you can draw. And what you might first do is ask, is there a characteristic size to these bursts? So essentially what you could do is you could just draw a bunch of these by eye and do a histogram. The more rigorous way to do that is do a Fourier transform of this. And what that gives you is an energy spectrum. So you can think about this a little bit like a PDF of these burst sizes, but I've done some prefactors and a squaring of that to give you what is properly an energy density. So you can think about this also as the energy contained in flow structures of a given size. And people in the literature just kind of invert this for a wave number because of Fourier transform. And what you see is that for the stable flow, you just kind of have this flat line here, and that's just because you have some experimental noise, but above the onset of this instability, you see this jump really sharply and show a power law decay, which indicates that you have a chaotic flow. And this is something very similar to what people see in inertial turbulence, but of course it's a different instability, so we have a different scaling exponent, which is interesting, but it shows you have a different instability, but there's perhaps similarities we can draw on. And I'll hurry up a little bit. I think we want to maybe move on. I'll just say kind of briefly, you can maybe look at the paper that we just published in Science Advances for the details of this, but the really, I think, cool thing you can do is not just draw analogies to turbulence, but kind of use techniques from turbulence to learn new things about this flow. And so essentially you can kind of follow the procedure that a turbulence person would have done to predict the resistance of these flows. I won't go into the details, but essentially what you find is that you expect to have a Darcy's law plus this new term. And we actually know what this new term should be if you do all the math kind of very carefully. And you can measure that at the core scale and see that above the onset, you see these bands of dissipation. And these represent regions where the fluctuations in your flow are causing viscous dissipation, much in the same way that inertial turbulence would cause dissipation below a Kolmogorov scale. And using that, we can now generate a model to predict this anomalous resistance. So here you can see Darcy's law, the resistance is on the y-axis, and as I increase flow rate, or Weisenberg number on the x-axis, you see that it deviates strongly at some point. And if I insert the model from that previous slide, you see that it agrees quite well. So I capture the onset and the growth quite well. It's maybe neglecting a little bit at the very end. We think we understand that as some extensional viscosity effects that we've neglected for simplicity, but this seems to be a fairly general thing across different media. I have two here, and there's kind of a third one that we have in the lab as well, that indicates that for spherical bead packings, this is a fairly general phenomena. So again, I invite you to look at that paper, but the real, I think, cool thing that I'll just finish up on is that we now have ways to relate an instability at the microscale to phenomena at the macro scale, and now we can begin playing with ways to control the flow in really exciting ways. And so I'll just show you the punchline of that and invite you to check out this paper on the archive. This was a collaboration with some really excellent undergrads, Richard Huang and Kelly Zhang in the lab, who helped me kind of sort through this. But essentially the trick is now we have a way to controllably increase the resistance in porous media by injecting these polymers. So I'm going to just show you, here's the kind of problem I posed at the very beginning, which is that the flow is too fast in the coarse layer, really slow in the fine layer. And you can help rectify this and homogenize the flow if you design your polymer solution such that the flow in the coarse layer is experiencing this anomalous resistance, but the flow in the fine layer is not. So the fine layer is laminar, the coarse layer is unstable, and as a result, you're slowing the flow down in the coarse layer and really speeding it up in the fine layer. So maybe I could just play those videos again, side by side, and you can see that the fine layer almost keeps up with the coarse layer, much, much faster than the pure solvent case on the top. So we think this is exciting, again, and we can kind of do some theory and predict where this optimum should be, which seems to agree pretty well with experiments across a range of media. So I just wanted to thank my team again. Thank you guys for listening. I invite you to check out these two papers. One of them is still on the archive for the kind of nuanced details. But I would look forward to any questions you guys have. Thanks so much.
Thank you, Christopher, for your really, really interesting presentation. And So now it's a question time. So please feel free to ask questions from the chat on the right of the YouTube video screen. We already have a question, so let's start from a question by Raid, the Himalaya. Nice presentation, Christopher. I was wondering if you are planning to study the effect of different core structures.
Yes, very much. So I think it's really interesting. Here, obviously, we just have different spherical brain packing centers placed in disordered, and we've changed the bead size. I imagine this would be very different if you, instead of having spheroid, had something more irregular. So that's something that we'd like to do. That gets really tricky with the way we do refractive index matching. It makes it much more sensitive. I certainly think it's interesting. And the other thing we're thinking about doing is ordering lattices. So here everything's disordered. If you have something that's ordered that you can fabricate, then that's maybe a nice baseline as well. And then you can kind of control by hand these individual things. So we're working with Simon Howard and Amy Schmidt at OIST who are helping us fabricate these channels, and hopefully you tune in for the next paper.
Nice, nice. And we have another question from Happiness Imwetinian. Thank you, Chris, for the presentation. On page 6, please, what technique do you use to visualize the process after refractive index matching?
On this slide? Oh, yeah. So, yeah, maybe I should have mentioned it. So, in these videos, you have so the raw data look like this. So you have particles in time. I, in these grade videos, am doing a little time blur. So I'm averaging over, I think, 2 seconds. So what you're seeing is an individual particle is tracing out a streamline, and that's just been blurred out. And then here, the particles are moving less far, so it kind of looks more like a dot. That's just to help your eyes. In the real analysis, we're using just the images of the particles and feeding that into PIV lab and MATLAB, which allows us to get Eulerian velocity field. Sorry for that unclear.
Okay, but I hope now you get more clear. And so we have another question. So a lot of questions today. I'm really happy about that. From Mamta Joktar. Do you think that this elastic turbulence would also occur in other types of non-Newtonian fluids, or it's something specific to shear thinning fluid? That's actually a question that I would have liked to ask. So thanks, Mamta, for this.
That's a super excellent question, and I think that's very important. So, so here I'll just remind you, though, we don't have a shear thinning fluid. We have Bruker fluid. So I guess it has a very light shear thinning. The shear thinning exponent is 0.93. So I don't think that that's really important. I think what matters is that you have an elastic fluid. So I think shear thinning is potentially fine. It's something that we certainly want to explore, and we're playing with solvent conditions, and it seems to matter, I'll just say. That's an ongoing project, but the shear thinning definitely matters and adjusts what this resistance looks like, but you still get similar flow behaviors and similar increases in resistance. I imagine this is something general to any fluid that creates instability of its own. So things like worm-like micelles certainly do this. I think a variety of different polymer chemistries would do this. And I mean, that's just a lot of really interesting things to certainly explore.
Yeah, and I might add, if there is some ill stress effect in this fluid, maybe there some strange effect might emerge due to the fact that there is this threshold to overcome. So I don't know if there is some ill stress fluid, so a fluid that presents not only a varying viscosity, but also ill stress that you should overcome in order for the fluid to flow.
Yeah, certainly. And I think what you'll end up seeing, if I'm just going to, because this is just really exciting stuff, I'll just speculate. You'll see this and other kind of cool flow effects kind of layering on top of it. So in yield stress, you might start seeing things like shear banding. You might see regions where you don't have any flow at all, like you have a locally solid region. I think that would be really exciting to look at.
Yeah, and quick question, always from Mamta Jokta, and I think then we can stop. Can you connect this result to potential BTCs?
To potential what?
BTCs. I don't know what actually Mamta is referring. Do you know? BTCs?
BTC, no, maybe he can.
Can I add just a quick question, like while maybe Manta adds what she means by BTCs? I suppose it's not Bitcoins, right? But maybe she can just write on the chat there. But just a quick question, Christian. So here you have like this fluid that has a constant viscosity, right? But this is not a Newtonian fluid, right? So how is this different from a Newtonian fluid? It's
Yeah, so the difference with the Newtonian fluid is that you can measure a normal shear stress. So what that means, at a fundamental level is that the polymer can stretch and store elastic energy, and that energy can advect. So you might call this like an Oldroyd B fluid. What that means experimentally, if I put this on like a cone plate rheometer and I'm spinning this, you measure a tangential shear stress. You also measure a normal force pushing up on the cone. And that is a result of this polymer elastic energy that's being stored and released in the vertical direction. And you can measure that as just one metric of this elasticity. You could also do a G prime and G double prime, and you would find that this had a significant storage modulus as well. Does that answer your question? I'm not sure.
It does. Thanks a lot.
Okay. By the way, Mamta refers to breakthrough curves as BTCs. So the question again is, can you connect these results, your results, to potential breakthrough curves? Breakthrough curves.
Oh, yes, breakthrough curves. Yes. I hope I put this as one of my backup slides. But so exactly, you would look at the breakthrough curves. Yeah, so here's two. I think this is comparing the solvent to the polymer at the same flow rate. Sorry, I've labeled this backup slide rather poorly. So this light green curve here is the solvent. And what you see is there's kind of two steps in this injection. And that's because it's really slow in the fine layer and really fast in the coarse layer. And if you now are running this experiment at what we've deemed the optimal condition to be, you'll slow down slightly in the coarse layer and speed it up in the fine layer. And so your breakthrough curve goes from being kind of two humped to something closer to one hump. But yeah, the breakthrough curve, I think, actually is what's telling you a lot of this information.
Okay,
excellent.
Okay. Also, okay. Thanks a lot, then.
Yeah, thank you, guys.
Thanks again. It was a long but very interesting question time. And so now I think we can move on. Thanks again, Christopher. And to introduce our second and last speaker of this session. So the next speaker is Zaid Jangda. Welcome, Zaid. And before starting, I would like to spend a few words to introduce Zaid. Zaid is a second-year PhD student in applied geosciences at Heriot-Watt University in Edinburgh, Scotland, and is working on underground hydrogen storage. Previously, he got a degree, both master and bachelor, in petroleum engineering at King Fahd University of Petroleum and Minerals in Saudi Arabia. In particular, he developed some experience with the imaging and also with the surfactant CO2 core fluiding experiments. And both these experience contribute to the current one, to the current his current job, and hopefully that can be his research can be an opportunity to contribute toward a net zero future. So Zaid, it's your turn, please.
Okay, I'll just share my screen. Hopefully you guys can see it. Can you see my screen now?
Okay, very good.
Okay, so again, thanks for the opportunity to present, and thank you, Christopher, for the very nice talk. So I will be presenting some of the recent experimental work we did, and I'm presenting on behalf of the whole team. So there's a big team effort behind the work. I will try to be a bit casual and hopefully not bore you all with too much data. And since it's a tea time talk, so hopefully everyone can enjoy a cup of tea or coffee while you're listening to me. So I would discuss obviously the interesting results that we got from these experiments, but there has been a considerable interest in the way how we perform the experiments as well in the backstory. So I would also like to touch base on that a little bit, and because I think sometimes it's not given its due importance, the preparation that goes behind lab experimental work. So just to start off, again, we are living in a climate crisis right now, and there are major changes that are required in all aspects of life to avert a disaster. So whether hydrogen energy is the answer to these problems or not, only time will tell. But currently, it is being considered as a major player in the efforts towards net zero. And this is reflected by the fact that just over the past few months, both the EU and the UK have significantly revised their hydrogen energy targets for 2030, which they had just set a year back. So in just a year, they have significantly revised them and increased the targets. If we take this huge requirement of hydrogen into consideration, we would obviously need large storage capacities, especially due to the cyclic nature of hydrogen. We produce green hydrogen and then store it and then use it when we are required at the most. So underground hydrogen storage is a potentially viable solution. Obviously, we have been storing natural gas, CO2 for a long time in the subsurface, but it has its own unique challenges. So we need to exactly know what will happen at the pore scale when we inject hydrogen into the subsurface and then produce it back. So this was the main objective of our work, and to see at the pore scale level what would happen at the conditions that would be in the subsurface when we inject or produce hydrogen. So we thought, okay, let's do some in situ flow experiments with hydrogen inside a HSCT machine. So maybe it seems straightforward, but obviously, again, we were in for quite a surprise. And then we realized slowly why no one else had done it before due to hydrogen and its safety problems and everything. So as I said earlier, I'd just like to share with you a little bit about the backstory that we had, which I consider as a roller coaster journey. And hopefully many young researchers, especially the experimentalists, can relate to it. So most of the times the preparation is much more time consuming and effort consuming than the actual experiments. So I think of it like as a queue to a ride in Disneyland. So the longest queues are mostly for the rides that are the most challenging ones. But the ride itself is very short, but then again you have the thrill of the ride with you for a longer time. So I just wanted to highlight this part as well. For us, the path that we had towards the experiment was also a very long one, and we had to get multiple approvals, especially for safety, because no one else had done hydrogen experiments at high temperature pressure. We were using hydrogen inside an X-ray machine, so we were doubling the risk, and it took a lot of efforts to reach that stage. But finally, once we reached the experimental stage, this is how our system looked like. We had a hydrogen flow cell inside a micro-CT machine. We had 4 different pumps connected to the flow system, and inside we also had a high pressure, high temperature reactor that was equilibrating the brine and the hydrogen before we injected into the system. And everything had been tested at high temperature, high pressure before we reached that stage. For our experiments, the plan was to conduct cyclic hydrogen experiments. We injected hydrogen, scanned it, and then displaced it with brine, and then scanned it. So after each stage, we scanned it. We started off first with a dry scan. Then we increased the temperature, increased the pressure, set the reservoir temperature conditions, and then we did our experiments. The difference here to note is that between the 2 imbibition cycles, the first cycle was done with equilibrated brine. We used a reactor to equilibrate brine and hydrogen for 24 hours at the experimental conditions before injecting it into the system to displace hydrogen. And in the next cycle, we just used non-equilibrated brine. So this is the important point to remember for the results. We were using a Bentheimer sandstone sample, and that was fitted inside the core holder. And then each scan, we managed to scan the middle of the sample. Once we finished the ride, once we finished the experiments, we came towards the results and towards the thrilling results. Again, to have these images also analyzed, it takes a lot of effort. And reaching from the raw image to the segmented image, or from A to C, here it is just on one slide. But I hope like people who work with imaging softwares can also probably relate here as well. So we took each data set and then filtered and segmented it to take out hydrogen and brine phase from each image. And once we had the results, I'll just show you one example of the 3D visualization that we got from the results. So here is just one example. So we have a state after drainage where we have injected hydrogen into a brine saturated sandstone. And we have all the three layers here shown. So once we remove the rock phase, we have the hydrogen and the brine. And if we just remove the brine phase, we see the hydrogen phase after drainage. So here we see that most of the hydrogen that we see is in a single connected ganglia and occupies the larger pore space, which is not visible here, but you can see it in the analysis. But it is mostly connected. And this was for both of our drainage cycles. I'm showing you right now the second cycle. When we displace the hydrogen with brine, so we inject brine from the bottom into the sample. And once the brine is injected, we see that the hydrogen, the large connected ganglia, has broken into small trapped ganglia. And obviously the saturation decreases. So this is this was evident in both of the cycles. But the difference in the cycles was, as I mentioned, that the imbibition fluids were different. And we see visually also that with equilibrated brine, we see high residual saturation of hydrogen compared to imbibition with non-equilibrated brine. And visually we see it here, and we also see it in the quantitative analysis that we did. So we have the saturation profiles here. Here you can see also, if we consider drainage, most of both the drainage cycles, most of the profile is quite similar. The saturation values are also quite similar. But when we go towards imbibition, we see there is a difference in the hydrogen saturation profiles. And also there is a difference in the saturation, the overall saturation. Again, why is that happening? I will maybe discuss it a bit later, but these are the results that we got. We also see a similar kind of thing in the pore radius comparison. Here we are comparing the pores occupied by the radius of the pores occupied by hydrogen after both drainage and imbibition. And we see that after drainage, again, the values are similar, the number of pores occupied are similar, but after imbibition, we see that a significantly less number of pores are occupied by hydrogen. So again, why is there the difference here? From our side, we think hydrogen is dissolving in brine, and we see it very clearly that there is a difference. Again, hydrogen is very complex. We still don't have all the answers, but we wanted to share what we observed in our experiments. We see that we clearly see that when we did the imbibition with a non-equilibrated brine, the residual saturation of hydrogen is less, the number of pores occupied by hydrogen is less, and it clearly posits that when we inject brine without equilibration, some of the hydrogen gets dissolved in that brine. So this is something that many people were not considering would be a challenge for hydrogen. And as I say here, that there are lots of complex challenges that remain for hydrogen. And before we reach the stage of implementing underground hydrogen storage, many of these challenges have to be addressed and have to be researched. There is lots of work to do for us as well, and hopefully we also plan to contribute further with more work in the lab and sharing more results. Again, I have not shared all the results here just because we have a brief time, but our results are out there available online, and anyone can refer to it. So I would just like to summarize the work that we did. And we saw hydrogen entrapment at high temperature and high pressure conditions. And we see that hydrogen trapping observed in preferentially the larger pores. We also have the potential dissolution of hydrogen in the brine, as we see less residual saturation after imbibition with non-equilibrated brine. So as I mentioned, the data analysis, the data and the results are available online. Anyone can have a look at them and also download the data and work on the data as well. So to study the dynamic effects, we also plan to do some synchrotron experiments and hopefully again share the results with you all. So I would like to end my talk here by acknowledging the people behind the work. They helped a lot in setting up the experiments, in preparation of the experiments. And I would like to thank you all for listening. And just before I shut up, I would just like to do one thing. Hope you don't mind. It's my son's birthday and I'm not with him there today. I would just like to wish him happy birthday. So feel free to contact. Thank you so much.
Wonderful. Happy birthday to Adil. Is it Adil?
Yeah.
Your son's name. Happy birthday to him, and congratulations both to him and to you for a very nice presentation. I think it's very nice that you also use this space to talk not only about the results, but about the challenge along the way. And this is the kind of thing that we who do experimental work, I mean, there's a lot that doesn't get visible, right? It's not really published on the methodology session. I'm not even sure like the things that work and how to do that, but it's a lot of time is spent on finding the thing that works, right? So it's very nice that you use the chance.
Thank you so much. It's also just to relate, like, if sometimes you discuss with people and just say, okay, just why didn't you just add one more experiment? So it's not just one experiment. There is the effort behind it.
Yeah. So I hope the theoreticians out there in the audience take notes.
I'm very lucky to have like a team, a supervisor who helps me in the lab. So it helps a lot.
Wonderful. Yeah, that's wonderful.
So much.
Very good. So we have some questions here. I have some myself, but let's go first to the audience here. So the first one is from Raid Himalaya. So he says, thank you for the nice presentation, Zaid. How different the physics of hydrogen flow will be from the other tested gases, example, methane, etc., considering density and viscosity. Will it be different?
Yeah, thank you, Raid. I think you answered your own question as well. So the properties are different. And again, like when people started to study underground hydrogen storage, there was some discussion that, okay, it would be just similar to CO2 and methane storage. We have been doing that for a long time. But hydrogen's properties are much, much different than that. It's the size of hydrogen is so small, it can just diffuse anywhere. So leakage is a big issue that has to be considered. Then again, the interactions of hydrogen, the chemical reactions that would occur, the microbial reaction that would occur when hydrogen is injected underground, all of them are supposed to play a role. So again, this is still a very nascent stage of study, and I think it's very good to see that more and more people are now starting to study with this phenomena because it would be needed. So again, all these are different challenges. Just one challenge of trapping is something that needs a lot of study. So there are so many challenges and so many different effects that would be contributing towards the flow of hydrogen. So again, it would be certainly different than the other gases when we inject it into the subsurface. I hope I answered. But again, I'm
sure
also
did. So we have another question here from K.U. Yan. How do you design the setup for high temperature and high pressure? For the image, do you use CT method? Thank you.
I thought I showed the setup there in the slides, but maybe you can also go through it later. So yes, we did use CT. So the challenge was, that's the main challenge, was to set up a safe setup inside the CT machine, with hydrogen, because again, like the safety is a big issue for hydrogen. So we managed to put a rotating stage inside the CT machine, and after whenever we finished an injection cycle, a drainage or imbibition, we scanned the sample immediately, and the sample rotated on the stage. So it was, we did use a CT method, and we used the core holder was a peak, so it allowed the X-rays to pass through, and we could see good images for hydrogen. That's why we use a very small core again, so that we can easily see the pore scale phenomena.
Yeah. So if I may add to this question, so the danger, is it that the whole thing could catch fire?
I mean, again, the most danger is because people are just uncertain. They have not used this. Again, the problem with hydrogen flame is that it's not visible. So if hydrogen causes fire, we won't be able to see it. So that was a main concern, and we just had to use very, very small amounts of hydrogen, and we had to fill hydrogen outside the lab. So these were all kind of things that had to be taken into account.
Yeah. There's a couple of things that we don't want in a lab. One of them is invisible fire, right? It's not really the best thing to have around.
Yeah.
So another question from Happiness Imwetinian. Nice presentation, Zaid. What is the actual temperature and pressure used? Did you experience attenuation of the X-ray signals? And if you do, how do you resolve them?
Okay. Yeah, so the temperature pressure conditions are mentioned earlier. We used 100 bar pressure and 50 C temperature. And those are the conditions at which we did all our experiments. For the X-ray, again, just for the imaging, we had to run lots of initial tests before the actual experiment. So we did many scans at different settings, and we selected the settings that had the least amount of any artifacts, so that our images could be resolved. Even though we could have changed the parameter of the settings to reduce the time, but then we just wanted to make sure that we get the right quality of images. So this also leads again to the initial prep thing, that just before the scans, we also have to do lots of iterations to get the right settings. And with our scans, we didn't see lots of artifacts, and we were able to significantly easily reconstruct and filter the images.
Super. We have yet another question from Olubukola Ishola. I love your talk. I was wondering if you could try to run numerical simulations to help understand the geochemical reactions. It can help clarify the question with the solution of H2 in brine.
I wish I could also do that. I do that. I think my supervisor will also be extremely happy if I can do that within my PhD. But just running numerical simulations with hydrogen is a major challenge. I think people are still trying to use the exact properties for hydrogen, and we have people in our team who are also trying to run those simulations. So if he has a simulator that can run easily, or if he wants to run the simulation, again, the data is also available, or if anyone else wants to run it. But hopefully someone from our team can certainly run, and then we get this answer also out.
Yeah, it's also hard to get one person to do everything, right? It's a lot of work, just what you did. So I just have just one quick question. So in the end, you said one thing that's hard here is that you're touching new territory, right? That's not something that there are many groups out there that know how to do experiments with hydrogen. This is all very new, so you have to find what works, what doesn't. So is from what you've learned, the parts of the setup that are used for other things, like the tubes, the valves, the connectors, all of these basic things. Did you have to change anything, or does it seem to work for hydrogen as well?
We had to order everything that was resistant to hydrogen.
Okay, so everything is specific to hydrogen.
Specific, and if you are using this, many things can be used, like similar things like the tubings and stuff, but you just have to be extra careful for the leaks, because it just leaks from anywhere. It's so small, so you just have to be extra careful with the leaks, and you just have to make sure that it works with hydrogen. Again, most of the things we had to order that were resistant to or compatible with hydrogen was also because of the safety clearances, because we were not allowed to use anything that could be just taken off the shelf. So we just had to be compliant on that as well and make sure that we satisfy the safety team.
Super. I don't see any other question from the chat. I think, do we have any other question from the audience here? We've had quite a lot, many questions today. So that was excellent. Very good session. So I think we can perhaps finish here. So we thank again both Zaid and Christopher. It was a very, very interesting session. And we already have our next session scheduled. So that's the second session. It will be on the 20th of September at 3:30 in the Central European time. So our speakers are Hongxie Li and Prane Shrestha. And yes, you can see the titles there. And we're going to advertise it again in all the usual channels. So thank you once again for joining us today. And stay tuned for the next Tea Time talk. And if you have anything, any comments, or if you'd like to subscribe to our mailing list, we have a mailing list for we also advertise all the future talks. And you can send a message to porousmediaTTT@gmail.com. And just one more thing at the end, we're always building a list of potential future members of the team. So if you think that this is something that you would like to do, you'd like to join the team to keep on organizing the talks with us, you can send your message to the email on the screen as well. And we're building this list more or less continuously. Super. Thank you very much once again, and I see you next time.